Welcome. So, this is the last lecture of module 11 where we are discussing the photoelasticity. So, photoelasticity is essentially a experimental stress analysis technique. Now, what we have learned basically is the Maxwell's law of stress and which relates the stresses and the refractive indices. So, what it states that the change or relative refractive indices is essentially proportional to the relative principal stresses. So, now it is we also express in terms of retardations. So, what does this retardation means? The retardation means that the if light is propagating in one direction, then to other direction, what is the relative phase shift. So, this is expressed in terms of, for instance, delta 1 2 is expressed in terms of the thickness and the stress optic coefficient C, and lambda is the wavelength, and sigma 1 minus sigma 2. So, this we also further modified in terms of plane stress condition. This plane stress condition, it is sigma material fringe value. So, this material fringe value if we know and if we know the relative phase shift that is in here, that is delta by 2 pi, then we can find out the change in the principal stress. And if we know the change in the principal strengths, if we want to know the change in principal strengths, then we have to use the relation between the principal stress and principal strengths. So, which will modify the material fringe value naturally, because the material constant will be plugged into that material fringe value. And we have seen that in case of a plane strain, the material fringe value will be epsilon is E by 1 minus nu into Fa. So, this we have seen, and if we used essentially the relation between stress and strain for the 2D plane stress material. But I want to emphasize here that here we assume that material is behaving purely elastic manner. So, there is no viscoelasticity or other thing is present. So, at least the number of at least the strain regime is in the elastic range. So, it does not go beyond that. So, that we have learned in the previous class, and this is due to the birefringence property or temporarily doubly refractive property of the photoelastic material. So, that states that when you have the isotropic when the material is unstressed, then the material behaves as a isotropic in optical property. That means the refractive indices are same in all direction, and when it is stressed, the refractive indices are different in different directions. So, this property is exploited for finding out the difference between principal stresses in 3 different directions when the photoelastic body is stressed, and this is known as the Maxwell's law. So, now here we will understand if the effect of a stress model in a plane's polariscope. So, this is the direction of the light vector. So, this is the analyzer and this is the polarizer. So, and here if we place the model, so you have sigma 1 direction, principal stress direction, and principal sigma 2 direction, 2 principal stress direction. Now, a plane model, when it is placed in a plane polariscope with its normal coincidence axis of the polariscope at an angle alpha, then the axis with the axis of polarization. So, alpha is the axis of polarization with the principal stress direction. Now, then the polarizing beam, we know we are very much aware of that this all optical, and that means the electromagnetic wave essentially we can express in terms of simple harmonic motion. So, this simple harmonic motion we express in terms of k cos of omega t. K is the amplitude, and when the polarized light enters into the model, light vector is resolved into two vibrations parallel to the two planes of principal direction. So, when the polarized light, also we know what is polarized light. So, this when we put the model under a polarized light, and then essentially it shows the this equation. Now, when this light expression, light wave vector along two principal direction we can decompose, which is k cos alpha cos omega t and k sin alpha cos omega t. So, this we know, and then as two component of propagation with two different velocity, because it shows since the refractive indices in two different direction will be different. So, naturally the two different velocity will occur in two different direction. So, that will lead to phase shift, and we have found out this phase shift delta 1 and delta 2, which is essentially this 2 pi h by lambda n 1 minus 1 and 2 pi h by lambda is n 2 minus 1. Now, this is the component of the light vector along the two different direction. Now, this we can further little modify. So, we can actually find out the what is the horizontal component emitted by the analyzer. So, the horizontal component essentially we can find out by just taking the difference, and this difference is expressed in this form. So, with this the intensity of the light we have seen earlier, that is what is intensity. So, E A x square, which we can represent in terms of this equation. So, this I is in terms of this, and then delta 1 delta 2 by delta 1 also we can write it in this form. Now, this is if you remember that this is the lambda by c is essentially material fringe constant, and so when I equals to 0, that means either this quantity will be 0 or this quantity will be 0. So, that means intensity of the light will be 0, is either this quantity will be 0 or this quantity will be 0. Now, the first condition of extinction of intensity is related to the principal stress direction, and other as the principal stress difference. So, we will understand what is this principal stress direction and what is principal stress difference. So, now, if I consider that the principal stress when this sin square alpha is 0, then what is the condition? So, now if when sin square alpha, when alpha is 2 alpha, that is the angle between the polarizer and the light vector is or the axis of polarization is essentially in pi, then one principal then naturally sin square 2 alpha will be 0. So, this intensity of the light will be 0. So, what this means, the one principal direction coincides with the axis of polarization, which is since the alpha is 0 and the intensity of light is 0. So, this gives us the extinction, first extinction of the intensity of light. Now, the fringe pattern produced by this sin square alpha term is known as the isoclinic fringe pattern. So, this fringe pattern is governed by the angle alpha. So, if you change the alpha, the fringe pattern will be different here. So, another case where the intensity will be 0 is possibly a sin square delta by 2 is 0, that is it is dependent on the relative phase shift. So, let us see, if sine square delta by 2 has to be 0, then delta by 2 is n pi essentially. So, what does this means? That when the principal stress difference is either 0 or sufficient to produce an integral number of wavelengths of retardation, then intensity of light emerging from the analyzer is 0. So, essentially delta can be 0 or it is n can be 1, 2, 3 and so on. So, if this is the condition, then this intensity of the light again is 0, and the fringe pattern produced by the sine square delta term is known as the isochromatic fringe pattern. Now, this isochromatic fringe pattern essentially, if you pass a monochromatic light, that is the light which is entering into the body, then we can actually get a very sharp fringes and very clear fringes. So, if we count the number of fringes, then we can actually find out the principal stress. So, what this is essentially with a monochromatic light, the individual fringe in an isotropic fringe pattern remains sharp and clear to very high orders of extension. So, if this is the stress optics law, and then n equals to delta by 2 pi. So, that means delta by 2 essentially n pi, then only the isochromatic fringe occurs. So, now if we now substitute this equation, then n is h c by lambda into sigma 1 minus sigma 2, and which is delta by 2 pi also we denoted by capital N, and then that is equals to h by f a sigma 1 minus sigma 2. So, essentially n is the number of fringes and h is the thickness, and f a is essentially the material fringe value, and sigma 1 minus sigma 2 is the difference between principal stresses. So, number of fringes appearing in a isochromatic fringe pattern is controlled by the magnitude of the principal stress difference, thickness and the material fringe value, and material fringe value is essentially the photoelastic coefficient, means photoelastic, the property of the photoelastic material, thickness, what is the thickness of the material you are considering, and so the number of fringes will appear based on the different, it depends on the magnitude of the principal stress difference. Now, this is a special case, and in most of the laboratory actually we use this property, and in the photoelastic experiment we actually count the number of fringes for an isochromatic fringe, and then we try to find out the difference in principal stress. Now, once we know the difference in principal stress, essentially we know the difference in principal strain, so we can also calculate the strain. But remember that at that time the material fringe value has to be changed, so it will be in terms of material parameter also. So, so the final, in case of a isotropic in case of a isochromatic fringe, that is the n is the number of fringe appearing in an isotropic fringe pattern, is essentially dependent on thickness, material fringe value, and these principal stress difference. So, finally, we can express it in terms of strain and strains also. Now, this completes our knowledge or our discussion about the transmission photoelasticity. So, where actually we can see the stress contour within the body, within whole body essentially. So, that is why it is a full field technique, or we can take the image of those thing and count the principal stress difference, and essentially we can find out the principal stresses. So, this can be extended to for 3D body, but as I have said earlier, in case of a 3D body, counting of such isochromatic fringe is a very tedious job, and finding out those principal stress differences is also a difficult task, but nevertheless it can be done. Another case where essentially you do not have the photoelastic material or the material which exhibits the birefringence property. There what we do, we use a birefringent coating. Essentially the coating material is a polymer essentially. Sometimes suppose you want to have you want to be tested a still body under photoelastic experiment. So steel is not a birefringent material, so it will not a non-crystalline material. So basically it will not show the birefringence property. That means it will not show the temporary doubly refractive property. So what we do in such cases, essentially we coat with a birefringent material, or we coat a layer of birefringent material on that body, and then we do the photoelastic material, and when the body is stressed, essentially the coating is also stressed. So the stress we get from that birefringent coating is the surface strain. So this procedure is also used in photoelastic experiment, where we really don't do with the non-crystalline material. That means the material which possesses temporary doubly refractive property. So this is another aspects of photoelasticity, which is not transmission photoelasticity. Rather it is we use a polymer kind of material on the surface of the crystalline or the crystalline body essentially, and then try to find out the stress pattern along the surface of the material due to the application of load. So this procedure also helps how the surface stress pattern will be in case of a complicated body. So here actually this completes our discussion on photoelasticity for this course. So photoelastic experiments is generally performed in all our courses in laboratory courses. So this theory is used there to find out actually the material behavior or the rather the stress strain pattern of the material. So in the this completes our this module, and in the next module we have another topic which is nonlinearity. So we will discuss the nonlinearity in the next module, where we will introduce what is nonlinear. So in theory of elasticity. So even though this is a nonlinear mechanics, or essentially the continuum mechanics is the next step of theory of elasticity, but we will introduce to you a basic concepts of what exactly nonlinear and why it is called nonlinear, and what is the difference with the linearized elasticity which we have studied till now. So I stop here. So we will meet in the next lecture with the introduction of nonlinearity. Thank you.